What is up, Dylan, and today we are going to dive into the world of time dilation. Now, this is one of the concepts of Albert Einstein's special theory of relativity, and it says the time for a person that's moving, we're going to denote that as T of S for time self, is equal to the time on Earth. We're going to denote that as TE, time Earth, right? Excuse my handwriting. My handwriting can be a little bad at times. But we're going to multiply it by this factor, which is square root of 1 minus v squared over c squared. Now, v squared, this is how fast that this T of S is moving. So, and this C right here, it's a constant, and that constant is the speed of light. C is the speed of light. So, now, we want these two to be in the same measurement because, so if V is going to be in meters per second, C has to be in meters per second. And if T of S is going to be in seconds, we want this to be in seconds. And so forth for minutes, hours. So, but what we're really going to get into is proving this. How do you get to this? How do you even come up with this? Well, let's start with an atomic clock, right? Let's do it like this. Let's imagine there is a mirror. These two things are mirrors. And we have a photon right here, which is a light particle. So it's going to bounce, it's going to keep on bouncing up and down between these. Now, let's say the distance between these two mirrors is L, and the time it takes for what going up and down once is time for self, because this is how we're perceiving the time in the ship. I forgot to say that this is moving at some velocity, v. But for us in this moving frame, this is how we will experience it. Now, for someone outside, they're going to see it a little differently. I mean, first, from here, we can see that T of S is going to be 2L over C. Because the time, because we know that we have time is distance over speed. So, and we can denote that because we know speed is distance over time, right? We can multiply t by both sides to get speed times time is distance. Divide both sides by speed to get t is distance over speed. So, really, T of S we denoted is is L going up and L going back down. So that's where this 2L comes from. That's the distance. And the C right here for the speed of light is the speed that that photon is going at. So that's how we came up with that. But how do we use that to know what the time on Earth is experiencing? Well, from an outside viewer, let's say he's right here, he's not going to experience it like this over here. He's going to see the light go like this. He's going to see it travel like that. Oh, auto draw. He's going to see the light bounce. He's going to see it go up and down, but he's going to see it move in position x-wise. So this is how an outside viewer is going to see it. And it makes sense, right? Because if this is moving, it would make sense that it does this if this were moving. Now, let's erase this and let's look at one of these. We already know that, well, this would actually be even. This would be exactly the same triangle because of reflection points. So, we know that this will be L. And if this is also going at of the same velocity v, we can denote that this distance right here is v times, let's say, t0 for how long it takes for this one to go up and down. Because, I mean, we can already see it's going to travel a longer distance. So this will not be the same as this. So we can say that t of s is not going to be the same as t of 0, because t of 0 is going to take a little bit longer because of the extra distance. So that means, alright, let's do this. Let's look at one of these. Now, we can say this is vt of 0 over 2, because we're looking at this portion right here. So this would be cut in half. Alright, and we can label this as h, so that means this must also be h. And we already know that this is L. So we can write, just by looking at this again, t of 0 has to be 2h over c. Because we already said that time is distance over speed. Well, we already know that c is the speed, so that's checked out. But the distance, going up and down, we have this h, it's traveling this distance to go up, and it's traveling this distance to go back down. So that's how we get that 2h. Now here's where it gets a little bit interesting, because we have a triangle. It's a right triangle. And h is our hypotenuse. So we can write h in terms of L and v and t of 0. But h is also up here. Now, what we are going to do is we are going to use a squared plus b squared equals c squared to see that vt of 0 squared, vt0 over 2, excuse me, squared plus L squared is h squared. taking the square root of both sides, we get that h is the square root of vt of 0 over 2 squared plus L squared. So we can just plug this right into this equation right here. And we will get that t of 0 is equal to, let me look at it again, 2 times the square root of vt of 0 over 2 squared plus L squared over c. Now, what we want to do next is find L so we can relate it to this equation right here. If we can find L, we're pretty much good to go. And luckily, we have L right here, so we can, and it's only 1, so we can separate it. So this initially is just multiplying by 2 over c, right? So we can just multiply this by c over 2 to get this. So c times t of 0 over 2 will be the square root term right here. Now, we can square both sides to get that ct of 0 over 2 squared is vt of 0 over 2 squared plus L squared. Alright, now we can subtract this term on both sides to get that L squared is equal to ct of 0 over 2 squared minus vt of 0 over 2 squared. Now, using this equation right here, we can isolate L. Again, because this is just multiplying by 2 over c. So we can multiply it by c over 2 to get that c ts over 2 is L. So we can plug that right in here. Alright, so we get ct of s over 2 squared is ct of 0 over 2 squared minus vt of 0 over 2 squared. Now, the great thing that I don't know, but I can see is we have t of s here and we have t of 0s over here. So right now we're already relating our time to the Earth time. Oh, what? I'm sorry. All of the t of 0s here, I meant for t of e, but t of 0 is technically t of e for this time. So I just really like using t of 0 because, yeah, it's an instinct. So t of 0 is technically t of e here. So t of 0 is Earth time. So what we can do here is we can simplify this. We can see that this is going to be, well, we have over 2's and squares, so these are all common, so we can cancel these out. Alright, so we get ct of s equals ct of 0 minus vt of 0. Alright, now what we can do is we can factor out a t of 0. You know, let's keep this squared because I am actually not sure if we can cancel these out. Yep, nope, I made a mistake. We cannot cancel these out, a matter of fact. We cannot. That was my mistake. Alright, sorry. So what we can do is we can just simplify this. We get c squared t of s squared equals c squared t of 0 squared minus v squared t of 0 squared. Ooh, I don't have a lot of space right there. Alright, we can factor out this t of 0 squared to get that c squared t of s squared is equal to t of 0 squared times c squared minus v squared. Now, we can divide both sides. Wait. Yeah. We can divide both sides by c squared here. I like that approach. So, now, to make this look easier, this is actually the same operation because dividing by c squared is the same as multiplying by 1 over c squared. So we can multiply it by 1 over c squared. 1 over c squared. The c squareds cancel here. And we get t of s squared is t of 0 squared. Distributing this 1 over c squared here, we get 1, that is not a 1, I'm sorry, 1 minus v squared over c squared. It's kind of looking like that thing that we showed earlier. All you have to do is take the square root of both sides and we'll see what we get. So we get t of s is equal to t of 0 times the square root of 1 minus v squared over c squared. Right there. Also, let's do a little extra proof. Okay? Let's do this. Let's divide both sides by this term right here. We'll get t of 0 to be t of s over 1 over the square root of 1 minus v squared over c squared. Wow. I just glitched out right there. So this is what we'll get for solving for t is 0. Now we know a fraction, your denominator of a fraction can't be 0, and a square root can only be positive or 0. So we can say that the square root of 1 minus v squared over c squared has to be bigger than 0. Now, if this were a regular square root, we could say equal to 0. But if this were equal to 0, it would be undefined. So we can solve this, and we will see that we get 1 minus v squared over c squared to be bigger than 0. And we'll get that 1 has to be bigger than v squared over c squared, meaning that c squared has to be bigger than v squared, which means that c has to be bigger than v. Now, what this means is your velocity can never travel the speed of light. That's, of course, if you have mass. So this shows that it's impossible to get to the speed of light, but you can get really, really, really close theoretically. But it will cost a lot of energy. So We can do a little bit of a bonus calculation here just to show how this formula works. Let's say you were traveling let's say if you were traveling, oh wow, what just happened? Alright, let's just erase this and put it back here again. Alright, t of s is equal to t of 0 square root of 1 minus v squared over c squared. Let's say we move this down, that's what I say. Alright. Let's say you are traveling half the speed of light. We will put that as we'll put that as 0.5 c. The speed of light is approximately, not exactly, but it's approximately 300 million meters per second. So that is very, very fast. So we will just use this for simplicity because if you want to look at the actual value, you can Google it and use that, but so if we use this as our approximation for the speed of light, 1/2 of the speed of light will be 150 million meters per second. I just put 150 meters per second, not 150 million. Alright. So, anyways, it will be 150 million meters per second, half the speed of light. So, let's plug in that value and let's see what happens. So, let's say 1 second passes for us. Alright, 1 second passes for us, so that will be t of s. Assuming that we are going at 1.5, what am I saying? I'm tired. Alright, my brain is glitching out so hard. Okay. Excuse me, alright. Assuming that we are traveling at light, and 1 second passes for us while traveling there, what will be the time on Earth? There we go. Okay. We plug in 1 second here, so that means that t of 0 will be in seconds, and we get 1 minus 0.5 c squared right there over c squared. So, if we distribute the squared on both sides, we get that this is 0.25 c squared, which means that we get the square root of 0.75. Now, we can use an approximation for the square root, and that approximation is that the square root of a number x is the square root of the nearest perfect square, so we can call that NPS, plus nearest perfect square, no, it's x minus NPS, nearest perfect square, over the square root, 2 times the square root of the nearest perfect square. So that's the approximation. Now, our nearest perfect square is 1. So, we get this to be the square root of 1, which is 1. We add 0.75 minus 1 over 2 times 1, which is 2. This will be minus 0.25. We can transfer this to minus. And this to be 0.125. So we get that it is approximately, well, this is just an 1/8 right here. So we know that it's going to be about 7/8 times, but we can say 0.875, whoops. So if 1 second passes for us, 0.875 seconds will pass for them, assuming that we're going half the speed of light. So if you were to go a minute, which is 60 seconds, we already know that it would be 0.875 of a minute. So if we multiply that by 60, let's do that calculation right now. Alright, let's do it this way. It's painful, but let's do it this way. We just gotta remember to divide it by the 1. Divide it by the... Yeah, divide it by the 1,000 and multiply it by the 10. Which means to just multiply it by 100, I believe. Well, divide it by 100, I meant, sorry. Alright, so 30, this is 42, 45, so alright, 48, so that's 52. Divide that by 100. So about 52.5 seconds. So that's pretty good for going half the speed of light. I was honestly expecting slower. But once you get in that 90% speed of light range, you're going to be going much slower. Maybe even 99% range. But that's still very fast. So that was my proof for this. This is just beautiful. I may have to keep this here. Well, that was my proof. If you want me to talk more about this, comment down below, like the video, show me any sign that you enjoy this type of content, and I will see you in the next video. Alright? I hope you enjoyed this video. See you in the next video. Dylan Knotts out.